Good morning to the esteemed guests and my fellow classmates and classmates. I'd like to humbly thank the organizing committee for giving me this opportunity. I've come here to deliver a seminar on the topic Math and Cryptography. Without much ado, let's dive into the session. Let's start with this. What is cryptography? By definition, crypt means hidden and graphy means writing. Cryptography is the skill of encrypting information with a set of predefined codes known only to the sender and the receiver as a means of securing information. Cryptography is done via various forms like math, algorithms, etc., and is used in everyday life from transactions to password storage. So before, so basically, how does math relate to all this? In order to have this information encoded, certain mathematical techniques could be applied. Say you want to encode this. Math is fun. How would you do that? You can say every alphabet would be shifted by 2. Or you can rewrite the entire thing by replacing every letter corresponding to the Fibonacci sequence into its reverse mirror, which would make it something like, let's say M would be shifted by, no, yeah, M would be shifted by something that's reverse from Z, which corresponds to the position of M from A. So by default, mathematics is highly involved in cryptography. These are simply basic examples, but math is also involved in stuff like cryptic algorithms such as RSA and Diffel, which we'll get to in a bit. So before going into different types, I'd like to describe what a key means. Key basically works like a pin or a passcode to crack your cipher. Simply put, it's the key to identifying the encoded message. In the previous example, the key would be Fibonacci sequence and reverse mirror. Basically, it tells us the way we can decode the messages sent encrypted. Now, let's dive into the types. First, we have symmetric key encryption. This basically involves just one key for both encryption and decryption. The key has to be provided with both the sender and the receiver of information for this to work. The algorithm encrypts the original message, and after it verifies that the receiver is holding the key, the algorithm reverses and the message is back to its decrypted form. This is comparatively faster than asymmetric encryption, which we'll get to it in a bit, and is much more efficient. Hence, this is used in bulk encryptions like bank codes and stuff. Secondly, we have asymmetric encryption. This involves two keys, public and private. One is used for encryption and the other for decryption. The private key is always withheld by the sender and the public key is, well, public, so everyone would have access to it. But the complete message can never be decrypted without the use of the private key. This is used in digital signatures and kind and is slower compared to asymmetric encryption since the use of two keys would involve a lot of processing and power. Sometimes people tend to use both symmetric and asymmetric encryptions. This is mostly used when secure information needs to be spread over a public source, say the internet, in bulk. Information can be distributed via public, I'm sorry, the information can be distributed in public via symmetric encryption. Then the verification of identity in order to access this information can be done via asymmetric encryption. Now let's talk about hash functions. This takes a numerical value, converts it into another shortened numerical value. The input value can be of any size, but the output is always of a fixed length. These have the power to convert a huge size data into small bits and are hence considered the building blocks of algorithms. This is a one-way operation. That is, the input you give cannot be deciphered just from the output. So like this is used to store passwords and digital signatures, which even though it's hacked, you cannot like get to know what's the actual password right from just the hashed ones. As we've seen above, math cryptography has several applications in several fields, such as military education and so on. A good example of asymmetric encryption, namely the RSA algorithm, works on the basic fact that it's hard to factorize a large number. The public key is a multiplication of two big prime numbers, and the private key is a factorized derivation of the same. The strength of the key lies in the size of encryption. The bigger the prime number is, the harder it is to crack the encryption, and the more secure your message is. If the hacker managed to crack the factorization of the public key that matches the private key, the information is no longer secure and your message can be decrypted easily. The Diffie-Hellman algorithm makes use of elliptic curves of the form y squared is equal to x cubed plus ax plus b. The algorithm uses this to generate points via intersection, that is, when two curves or two public keys in our case intersect, and the points of intersection would be taken and converted into another secret key. This is used to share secret information through a secret network but on a public platform, let's say the internet. So basically, this uses two public numbers, say P and Q, and two private numbers like A and B. These numbers are used to form curves like x is equal to g to the power a mod p and y is equal to g to the power b mod p. Then the public keys are exchanged and the private keys are found out via the point of intersection of these curves. That is, A and B can be found out when the x and y intersects. Thus, we can see how big of a role mathematics plays in cryptography. Like Shakuntala Devi said, everything around you is mathematics, everything around you is numbers. Math extends to every part of our lives, including security, as I told you in my presentation. With that, I'd like to end my seminar. Thank you so much for listening.
Okay, any questions? Yeah, Ajay Krishnan.
No, sir, I was just appreciating, not any question.
Okay. Okay, so thanks, Ragvishi.